Assalamualaikum warahmatullahi wabarakatuh. I'm back to my panel 1, Dr. Muhammad Indra bin Khairi, and my panel 2, Dr. Junaina binti Sardi. I'd like to thank my supervisor, Dr. Hafiz bin Salim, that has been given guardians throughout my final year project too. Um, First of all, my name is Muhammad AZUAN bin ALLIAS, and I'm going to present you the final year project 2, which investigation on initial response and frequency regulation in a power system. Okay, for the introduction, the increasing population makes the utilization and demand of electricity increases. The renewable energy source is widely used to reduce dependence on conventional generation and support the main grid. RES, such as wind turbines, provide low emission system, and photovoltaic provide zero inertial systems since they do not have a stored kinetic energy. Microgrid are distribution networks consisting of distributed energy sources like photovoltaic and wind turbine that been one of the most popular. The increasing penetration of RES challenge power system stability in a term of frequency stability. Next is the simple single diagram of a grid system with a renewable energy source participation. As we can see that the power from generator is generated by the generator itself, go to the bus bar, go to the transmission line, go to bus bar, and lastly go to the load. What we can see here that the RES is commonly connected at the load side, which give additional support to the load if there is a contingency. Okay, uh, here we can say that the power generation equal to power load, the frequency will remain constant, and if the power generation over the power load, the frequency will be high, and if the power generation below than power load, frequency will be low. Okay, problem statement for this project is a RES provide low initial system that can return frequency stability when sudden disturbance occur. Second one is intermittent RES output power may affect the conventional grid system, and major problem from a frequency fluctuation of the grid may occur. And the third one is it is a challenge to control the frequency excursions toward achieving the frequency balance. Okay, there are three objectives. First one is to investigate the frequency response in the system. This has been made in the PSM1. The second one is to study the initial response and frequency regulation on a grid with a participation of RES. The third one is to improve the frequency response for the microgrid system. Okay, the scope of this project is we use a synchronous generator and wind turbine because as to study the initial response and frequency regulation, synchronous generator and wind turbine are commonly used to to see the direction of the initial response. RES that we use is a wind turbine. Sample microgrid system is applied to study the frequency response in the system. The software used for the simulation is a PSCAD. Okay, next for the literature review. I bring you a three impact of renewable energy sources toward frequency stability in power system. First is a behavior of the system frequency in terms of rate of change, rock-off, and frequency nadir can be varied by the integration of RES. Second one is a RES provide low initial system and reduce governor response because it provide less rotating mass, which is main source of inertia. The third one is the fluctuation of the output power of RES, which depend on the natural changes like irradiation from sun, wind speed from wind, may affect frequency regulation due to the imbalance of a real power between generation and load. Okay, for the issues in the for issues for the initial response and frequency regulation, and non-synchronous RES provide low initial system that can trigger the higher rock-off. The method to solve it is to implement the fast frequency response service, which and develop small signal analysis, which can be found as a maximum rock-off. Next one is a microgrid facilitate more dynamical inactive power during contingencies, but affect severe stability issues such as frequency stability. To avoid that is FCR, frequency control reserve strategy, is applied to minimize the frequency deviation. The next issue is increasing output power of wind turbines proportional to the frequency deviation. So to overcome that, synthetic initial strategy and group control strategy is applied. But the optimal parameter tuning for both method is important to enhance the frequency response. Okay, for the methodology, there are 4 cases that I'm going to discuss. The first one is a initial response with a 4 type of generation configuration. Okay, the first generation configuration is a single generator. The second one is a wind turbine. Third one is the 2 generator. The fourth one is a 2 generator, but one is a synchronous and one is wind turbine. As you can see, the parameter here is stated here to build the system for the case 1. Okay, here there is a schematic. There is a system for four generation configuration, which we can see the initial response when disturbance occurs on 10 seconds of the simulation. Okay, for the case number 2, the simple microgrid system with the penetration of 2 unit wind turbine and 1 single synchronous generator is built. The case number 3, simple microgrid system with penetration of 3 unit wind turbine with a 2 split unit commitment for the wind turbine. Okay, for the case number 4, simple microgrid system also, but the penetration of wind turbine is a 4 unit, which is 2 is classified as a split unit commitment. Okay, there are 4 cases that will be discussed. And for the result and discussion, for the case 1, we observe the steady state condition first in where no disturbance, and we found out that the wind turbine has a highest tolerance, which is not good to the frequency regulation, and the 2 synchronous generator has the better tolerance, which are good for the grid frequency system. Uh, for the disturbance occurs at 10 seconds, sudden load change occur to observe the initial response of the system. So we can see that all the 4 generation configuration initial response here. So from the data, we can know that the 2 synchronous generator has a lowest tolerance, which give a good initial response, and the frequency is the highest. For the case number 2, we put the disturbance at the 10 second, and we observe the frequency nadies and the tolerance. It is stated that 0.07 seconds are taken to recover the initial response to the steady state condition, and the frequency is a 49.8778. Okay, the case number 3, the disturbance seems like before, and the frequency is 49.827, which is more better than a case number 2. Okay, for the case number 4, with the with the different type of generation, we can know that the frequency is a 49.814, which is the case number 3 is better, but what we expect is a case number 4 is better than case number 3 uh, because there are many generation which 4 unit of wind turbine and 1 synchronous generator that can store high kinetic energy, but theoretically fewer uh, initial system stored in generator, the easier the initial effect to return to steady state condition. We can see that the time taken to be in the steady state condition is a 0.125 second. Okay. As a conclusion and recommendation, for increasing number of renewable energy source in the conventional grid system may trigger power system stability. Initial response for RES generation is in a low level compared to the synchronous generator. Frequency nadir can be improved by using a correct method when the RES takes place in the grid system. The result of the simulation shows that the penetration of RES into a grid may reduce time response to return the steady state condition. Okay, for the recommendation, study on an initial response of the other type of generator and wind turbine need to be conducted for future reference, and the effective control technique to improve frequency response during contingencies and unwanted event, even though the penetration of RAS is high, can be done and can be studied in the for the future response. Okay, I think that's all from me, and uh, I like that's all from me, and thank you for uh, for watching.